Problem 16.52. In this problem, we consider a sealed 20 centimeter high electronic box whose base dimensions are 50 centimeters by 50 centimeters placed in a vacuum chamber. The emissivity of the outer surface of the box is 0.95. If the electronic components of the box dissipate a total amount of power of 120 watts, and the outer surface temperature of the box is not to exceed 55 Celsius. We need to determine the temperature at which the surrounding surface must be kept if the box is to be cooled by radiation alone. Assume that the heat transfer from the bottom surface of the box to the stand is negligible. Note that it says that the box is placed in vacuum, which immediately tells you that there is not going to be any cooling due to convection, since convection requires a medium. If we evaluate the surface area, or the area that is in contact from the fluid or in vacuum for the box, notice that we have basically a box, and we're going to consider 5 of the surfaces. 4 that are going to be on the sides and 1 that is going to be in the top. So the area that we are going to evaluate is going to be the top, which is basically 0.5 times 0.5 plus 4 of the side surfaces, which have a height of 0.2 meters times the length that it has of 0.5 meters. Okay, therefore in total the area that is in contact, or that is exposed to cooling, is going to be 0.65 meters square. As we said before, we're only going to have heat loss due to radiation. That is equivalent to epsilon, sigma, the area, the temperature of the box, the surface temperature to the fourth, and T surrounding to the fourth. Okay, what we're looking for is the temperature of the walls, basically the T surroundings. So we're gonna solve this equation. We're gonna leave it as T surroundings to the fourth, and we're gonna simply say Q radiation epsilon sigma A plus T of the surface to the fourth. Okay, and this value is negative. Okay, so now let's substitute the values. Once again, we're gonna keep it to the fourth, and then we're gonna do the solution in a second. So this becomes 120 watts divided by emissivity is 0.95. The Stefan Boltzmann constant is 567 times 10 to the negative 8 watt m squared Kelvin to the fourth. The area we calculated to be 0.65 meters squared. Okay, and the surface temperature, we had it as 55 Celsius. However, it needs to be done in Kelvin because we're doing radiation. Therefore, it becomes 328 Kelvin, and this goes to the fourth. Okay, so we're gonna do both of the components. Once again, this is to the fourth. This part over here, if we plug it into the calculator, it becomes negative 3.427 times 10 to the ninth. Okay, and if we see the units, watts cancels with watts, meter square cancels with meter square. What we're left with is Kelvin to the fourth. And this value over here, 328 to the fourth, becomes simply 1.157 times 10 to the 10th. And once again, this is Kelvin to the fourth. We add these two values, 2 surrounding to the fourth, and this becomes 8.147 times 10 to the 9th. And this value will give us this, this is simply Kelvin to the fourth. And then now to get the value of the actual temperature, we're going to take both sides and we're going to power it to the 1/4, so that the 1/4 and the fourth cancels. So T surrounding simply becomes 300.43 Kelvin. Okay, or if we write it in Celsius, this is going to be 27.43 Celsius. Okay, Please remember that when we are doing radiation, you always have to do it in Kelvin. And notice, since I'm looking for a temperature to the fourth, I did the solution at the end just to avoid any issues with algebra.